Hi everyone, the next topic is testing. In the previous videos, we do estimation on linear models. So we estimate beta, and our estimate is beta hat. So now that we want to see if some hypothesis is plausible or not. And the first testing is a t-test for beta I is equal to 0. Whether or not the beta I is equal to 0 is often of our interest. For example, suppose y is the chance to get some disease and x is the BMI of a patient. Then often we want to see if the BMI positively affect y, negatively affect y, or BMI doesn't matter for the disease. And this test is based on this theorem, theorem number 3. So suppose that epsilon j follows normal 0 sigma square for all j's and IID. So we should have very specific assumptions on epsilon j. And if beta I is equal to 0, then this quantity, beta I hat minus 0 over variance of beta I hat, this follows t distribution with degrees of freedom n minus p. So beta I hat and variance of beta I hat have been estimated in previous videos. So using these quantities, you can construct this statistic t, and this capital T follows t distribution with degrees of freedom n minus p. So here t distribution is symmetric distribution centered at 0. So it's similar to normal distribution, but the difference is that t distribution has heavier tail. So at the tail part, the t distribution has larger value. And the t distribution is actually a family of distributions, and degrees of freedom, depending on the degrees of freedom, the shape differs slightly. Degrees of freedom is smaller, so heavier tails it has. And degrees of freedom goes to infinity, it approaches to normal distribution. Yeah, and using this theorem, we test the hypothesis by this p-value. So remember that the p-value is the probability that more extreme event happens under the null hypothesis. So if p-value is small, that is our observation is our sample is very special if the null hypothesis is true. So that means the null hypothesis is not likely to be true. So that means, okay, so this t statistic is basically beta hat minus 0. So basically beta hat. So if beta hat is far away from 0, we are likely to reject the null hypothesis that true beta I is equal to 0. But of course, it depends on the variability of beta I hat. So we have divided this quantity by square root of variance of beta hat. So that means if the statistic t falls in typical range, such as here or here, then we don't reject. But the t is very extreme, and if t exceeds some threshold, then we reject this this null hypothesis. So this is the idea of the t-test. Okay, so this is an example in R. This is actually a repeat from the previous slide. So we fit a linear model. So we regress the undercount on percentage voting for war and percentage of African American. Then we have estimate here. So these are beta 0 hat and beta 1 hat and beta 2 hat. And this is standard deviation of beta 2 hat, the 0.0374. Then this t value, so this is the t statistic. You can see, so this value is actually t. So that is the 0.02853 beta 2 hat divided by standard error of beta 2 hat, so 0.03074. So this is 0.928. Then if we think about the t distribution with degrees of freedom n minus p, actually n minus p is here, 165. So if we have t distribution here, degrees of freedom is pretty high, so it's almost normal. And if we think about 0.928, the p-value is defined by the total of these two areas. So these are p-value. Since 0.928 isn't very large number, p-value is not very small. P-value is actually 0.35. So for example, if we use 5% significance level, this p-value is larger than 0.05, so we do not reject null hypothesis. So we don't have any evidence that percentage of African American affects the undercount of the presidential election. And the same thing for beta 1 hat and beta naught hat. So usually intercept, people don't care about it much. Sometimes it's important to check if intercept is equal to 0, but often this is ignored, and we are interested in the significance of beta 1 hat or beta 2 hat. So the next one is the confidence interval for beta I. So this is actually the estimation and not testing, but it's related to testing. So I put the materials here. So 1 minus alpha confidence interval for beta I means that interval includes the true parameter value, beta I, with a probability of 1 minus alpha. So usually alpha is small number such as 0.05. So 95% confidence interval includes true parameter with 95% probability. And that interval is given by this. So almost similar to the t-test formula. So beta hat plus minus the t quantile point times standard error of beta hat. So here the t superscript alpha over 2 subscript n minus p. So this means when we have the t distribution with degrees of freedom n minus p, okay, so this is t sub n minus p, and alpha over 2, so that is this point, and this area is alpha over 2. So this point is called t sub n minus p superscript alpha over 2. So this number. And 1 minus alpha is called a confidence level. So alpha is typically a small number such as 1%, 5%, or 10%. In R, you can use the confidence interval, CONFINT function, and you can put a linear model. I think that this is a linear model object. Then you can specify the confidence level. So I specified 98%. So 0.95 is default. Often people use 95% confidence interval. And intercept, for intercept, the 98% confidence interval is this. So at least you can see most of the time, I mean, we are 95% confident that the intercept is actually between these two values. So at least more than 0. And percentage who voted for Gore, so that is here. So this confidence interval ranges from a negative value to positive value. So actually we can say it's not clear which direction that this affects the undercount. And percentage of African American, the same. So it doesn't really, it isn't really clear which direction that it affects the undercount. Okay, so we discussed the t-test and confidence interval. So basically that we used the same theorem and we derived both and we discussed examples in R.